you have any question, always feel free to ask because classes are not a one-way traffic. The cars will only go should be a both way. So that's another point you should ask questions. And another thing I always try to say to students that I know that when I started teaching in 1985 and today when I am see, 13th of August 2021, a big change has happened. That's the internet, the information that I always jokingly used to say that when we were students, we used to pray to Lord Vishnu, Lord Brahma, that please give me this thing. But at your age, in your time, you only pray to Lord Guru, and within 1 second you get it. That's the big change that has happened, and that has affected teaching also because during our time there was no internet, nothing. So it was only the books and maybe a few journals in the library. But for that you have to go there, and you will be laughing at me that in 1981, 1982 there was no Xerox machine. I mean, that is the that is the hard fact of life. We didn't see the Xerox machine or photocopy machine. It was just coming up in 1983 or 84. It's coming up, at least in book. So we cannot Xerox it also. We have to handwrite, from the book or the journal. Anyway, that was our time. So then teaching was also different because we were dependent on the teacher who were taking the class. Then we used to take the notes because I know that there will be no soft copy with mail, so I have to take the note and so on and so forth. So attending the class was very important. Otherwise, I will not get the notes. Sometimes I will take it from a friend, but I don't know whether the friend has copied properly or not. So there was a lot of questions. Whereas now things have completely changed. Anything that is there in your syllabus, you type in Google, you will get everything. In fact, you get so much. You will be, in fact, confused that which one to take and which one not to take. So when all this information is available to you, and I am 100% convinced that if there is an equation to be developed or used, you are much better than me. And I have no doubt about that. You can deduce the equation faster than me, better than me. So given all that, now the big question is coming: why you should attend my class? Now that's a very big question. Why my students, now 20 students I see in my class, why they will attend my class? Anybody can tell me why you should attend my class? In today's world, when all the information is available, just not for attendance, don't tell me that.
Sir, so that we
So
can
to understand,
Yes, let me.
so that we can ask our questions directly to you and get
So,
the
what
right
you are,
answer.
so you are trying to tell that to get the clarifications on some certain issues. Right? So that is what Rahit is saying. Anybody else?
so also to understand it better and in a more compact way, because when we see many things, it is difficult to comprehend. But when someone is teaching, we may
Yeah.
understand it better.
Okay. So Ankit is giving an. Is it Ankit or Anish? Who was it?
Anish.
Anish. Okay. Anish was there. That was Anish. Anyway, so there you can see that these views are there, and I have a view which I follow in my teachings. That is, see, again I am going back to engineering. See, I am going to teach you something, and when I was trying to teach, I told in the third year, I told the same. that whatever I am trying to teach you, or going to teach you, I have to correlate it with the practical scenario. Because unless you know that where or under what circumstances this is useful, then it doesn't really become useful. I fully understand. Just solving one problem is not interesting. But if I can tell you that by solving this problem, you can also approach this practical. So it's the relevance of what you are being taught to our practical life. This is the essence of today's teaching. If I cannot do it, then you will not attend my class. I am 100% because you will not be really attracted. And then I can always complain that students are not attending my class, etc., etc. But then I have to think about myself, that how I am teaching. So I always try to teach from that angle. And I teach from my very long time. I teach from third. That's the second year plus. But in your case, I was not there, so I didn't teach you. But for this year's second year students, I was teaching theory. And I was telling them the same thing. I was telling that, field theory class, what is the first impression that comes if you close your eyes and think about field theory? I think most of the time you will have a horrific view of lot of, Taylor operator, curl, divergence, is that. Field theory is something like this.
Yes,
I
sir.
am, isn't it?
Yes, sir.
Um, but that's the entirely wrong notion. It's not. Field theory is not a tail curl divergence. Field theory is also something which is happening because this world, whatever is happening, it is primarily the interaction between electric field and magnetic field. So all these Dale curl or whatever it is, they are trying to explain something which is happening. So it's not that field theory we start from a Dale curl and then explain what is happening. Rather, it should be reversed. First, we have to say that look, this is happening, and then I can explain it with the help of all those curl divergences. Then you really get the essence of the field theory. That this is not something so abstract. But this is actually where we go wrong. I mean, we means teachers go wrong. That we sometimes also get confused and we highlight only the mathematical part. Because, I mean, that by that I can show my knowledge also. I can do this and that. But at least to me, that is not the way to teach. And in your this course, I'm again going to teach a lot of theoretical stuff. This is called numerical field computation, then analytical field computation. There will be a lot of mathematics. But should I start from the mathematics? My answer is I will not start from the mathematics. I will try to start from the physical point of view, that why I am going to do this. And then I will try to say that look, this cannot be done by anything else, so I have to do this. For that I will need this mathematics. So mathematics is purely a tool. In our case, it's purely a tool to explain something which you will be doing in your real life. That is my approach of teaching. This is the subject title, the voltage technique of what I will be teaching you is purely on the high voltage fields. Again, as I said, that the moment I say high voltage field, you might get terrified. That again, a lot of this that will come. No, you will see that when I try to explain it to you, I will try to make it down. But for that, probably you have to attend the class. Otherwise, you will not get the concept. Because just reading the notes will not be possible. Of course, mathematical derivation you can understand. Okay, now I should give you an introduction. Today I will only give you an introduction. So let me first show you this part. We hope it will come on the screen. I think it is coming on the screen. Can you see it?
Yes,
Yes,
sir.
sir. Yes, sir.
Yes. So now you can see that this is like a numerical calculation. Now, first question again is why I am computing the numerical, or rather just change it. Why I should know electric field? Any idea? Why I should know this?
Sir, because electrons move along the electric field and the voltage is also developed along the electric field. So, for any kind of work, we should know about it.
Okay, this is more of a theoretical answer. Anybody else? Okay,
The
let me put it.
insulation
Yeah, yes, please. Please.
insulation depends on the electric.
Now you are slightly on a practical approach. Okay, but insulation depends on electric field. It's a slightly vague statement, so I may explain it. But you are slowly coming to the practical side. That's what is important. That grasping the practical side. Okay, first I will ask you a very common question for an electrical engineer. I think you have done that very experienced. What is the difference between breakdown voltage and breakdown strength? Difference between breakdown voltage and breakdown strength. Or rather, is there at all any difference? Anybody? No idea? Everybody is silent.
Sir, breakdown voltage is particular to a particular kind of material. Like what is the thickness? Depending on the thickness and other
Ah,
specifications, you can say the breakdown voltage. But breakdown strength is intrinsic property of the material.
very good. Now you are very to the point. Yes, correct. So let me explain it in this way that you take a paper sample. Paper is a good insulator. A paper sample, and that paper sample has a thickness of say 1 millimeter. So I test the breakdown, I get a voltage, then at this voltage breakdown. Then same paper sample I can take with 3 millimeter thickness. If I do the test, now breakdown will occur at a higher voltage. So you can say that breakdown voltage depends on the sample. Whereas breakdown strength is not so. It is as rightly pointed out by Anish that it's an intrinsic property of the material. That if I have paper one as the material, then breakdown strength is its property. So, I mean, then now we have to understand what is the problem. So then we have to think that if the breakdown voltage varies with the thickness, sample, etc., then can we not do it that what is the breakdown voltage per unit length? Now that will not be dependent on sample because we are taking per unit length. The moment I say the breakdown voltage per unit length, you can see that the unit of the quantity changes. It is no longer volt. It is volt per length. Do you remember what is volt per length? Is it electric potential?
So,
Hello?
volt per length is field.
Yes. Volt per length is the field intensity, electric field intensity. So therefore now we can see that breakdown voltage is actually representing electric potential, whereas electric breakdown strength is the electric field intensity, which means that every material has its withstand capability that it can withstand up to a certain highest value of electric field intensity. If you go beyond that, there will be a breakdown. So therefore, for breakdown, it is not important that we know the breakdown voltage. It is more important that we know the electric field intensity. And therefore, for a particular equipment, whether that will be able to withstand the voltage. Let me say I am designing a 132 kV transformer. Now it is not important what is the voltage. It is important that at different locations, what are the electric field intensity. Accordingly, I have to put the insulation because the insulation has to withstand that electric field intensity. If it exceeds the breakdown strength of the insulation, there will be breakdown. Machine will fail. That is the significance of knowing electric field intensity. And second thing is, it also helps in improving the design of the material. Sorry, not the material, improving the design of the equipment. Because if I want to optimize, because today optimization is a major aspect of engineering. Now, how do I optimize? Optimization is like that my insulation, if its breakdown strength is very close to the electrical intensity at that location, then you are fully utilizing the capability of the. Say, for example, a material has a breakdown strength of 30 kV per second, but you are using it at a place where the field intensity is 15 kV per second. So you are using only 50% of that capacity. But if I use it, if the field intensity is 25 kV per second, then you are almost using 80%, and the rest 20% you keep for the safety factor. This is called optimization. But for doing that, you also need to know what the electric field intensity. Now you can ask me that why should I compute? I can measure it. We have all sorts of sensors today. Yes, of course, you can do that, but there is a big issue. What is that? The issue is the measurement of electric field intensity needs some sensor. Now, at any location, if you want to measure it, the moment you put the sensor at that location, then the configuration changes because the sensor is a material. You are putting something new in the overall system. So the field intensity in the absence of the sensor and in the presence of the sensor is different. So therefore, what happens? It is extremely difficult to measure the electric field intensity in situ, that means at the site of the launch. That's a very big problem of field intensity. Therefore, we need to know the electric field intensity in the indirect. That is why, these are explained here some basic things. So there are a lot of efforts have gone into this electric field distribution determination because the electric power equipment that is that was developed from late 1900, that is 1890 onwards. But at that time there were no computers, nothing, so people were totally based on, you can see the first one, that methods based on experiment. So people used to build small models, do experiments, and try to find out the capability of the installation. That was time consuming, not very accurate, but at that time it was okay. Then slowly people started developing other techniques. One is the graphical method. I will try explain at the very end of the course very briefly because nobody uses it today. But it's a very interesting method where the development of the models were not there because model development, and remember this is not software model. Model is actual. These are very time consuming. So people used to develop some graphical technique where you can use some ways where these models are not. Then the third one is the analytical method. Analytical method, even today it is used because this this is the method which is 100% accurate. And but there is a problem. What is that problem? That this is possible. That this analytical method is possible to use only when the geometry can be explained or rather written in terms of well-known equations. For example, if I have a sphere, I can write the equation. If I have a cylinder, I can write the equation like that. As you know, the practical life, the geometries are not only sphere or cylinder or disk, there are a lot of complicated geometries. So in those cases, analytical methods very difficult to use. But still today, analytical methods are used as a benchmark in many cases because somewhere you have to compare the results, so you need a benchmark. For that, we use still today we use the then came the numerical methods. It all started from 1960s. Even in 1960s, computers that time were not there, but people started developing things. These techniques can be primarily divided into three groups. One group is called differential equation techniques. I will teach you this technique in this course. I will go through two different methods. The first one is called finite difference method or FDEM. That was the first one developed long, long time back, 1960s. But no, immediately people understood there are problems with finite difference method. So then came the finite element method or FDM. And this is so powerful that today, in fact, all problems what we attempt here is basically solved by finite element method. The softwares that are available today as a commercial package are amazingly powerful. I am sure at least half of you during your career in some way will be using FEM tool. 100% because it is everywhere. Everywhere in engineering, FEM tools are used. And just opposite to differential equation technique, there is something called integral equation technique. The first one to be appearing is chart simulation method. This is actually developed in Technical University of where I taught. In 1974, it was proposed. Then it was developed into a further one is called surface chart simulation method. And finally, it evolved into boundary element method in 1990s. When I went to Germany, I worked on boundary element method. And in 1980s, when I did my PhD, I worked on gas simulation methods. So this area is very close to my heart, and I will teach you charge simulation method also in this course. What I will not teach is the third category. It's called Monte Carlo techniques. This is used for plasma because you know the materials are four states: solid, liquid, gaseous, and then plasma. But plasma field is also required, particularly in nuclear engineering or rocket science. So here we use Monte techniques, but this will not be taken in this particular course because in this course we are mostly talking about the power engineering. Now, when we discuss about so many methods, one question will appear that if I solve the same problem by three different methods, in all probability the results will be different. Now, which one is correct? That's a very big question. Basically, what we do with these methods, for that you know the fundamental of field theory that the equation that we solve is primarily, by the way, I am talking about electric field, not magnetic. This equation, as you can see, 13.3, and don't bother about 13 because I have taken this from my book. I have a book on electric field theory which is published by Taylor and Francis, CRC Press. But there is no Indian version, so it is very expensive. Anyway, uh, you can say del square phi is minus rho v by epsilon. This is the Gaussian summation. Any you can call it Gaussian summation. And when the volume charge density is not there, it reduces to del square phi and 0, and this is called the Laplace summation. So either we solve Laplace's equation or we solve Poisson's equation. Now, which method is correct? If that question comes, then there is a lot of debate because people will always say my method is. For that, in electric field theory, we have a theorem. This is known as uniqueness theorem. Have you studied it in your field theory course? Uniqueness theorem in the third year? Sorry, second year?
No, sir.
No. It's unfortunate because I always teach uniqueness theorem. But this is so important to understand the. Anyway, uh, what it says, I will not go into all the statement of the fundamental thing it says is that uh, if we solve either the Laplace equation or the Poisson's equation, two basic equations, then there is a very big condition subject to boundary condition. By the way, all our electric field problems are called boundary value problems because our problems are always defined by what are the values of the boundary. For example, what is the potential of the boundary? So on and so forth. These are all called boundary value problems. Please remember these terms. It helps you in other form. Even later on, when you be sitting where 10 people are discussing and somebody suddenly says, in this boundary value problem, this and that happened. Now you will start thinking, what is this? Is it coming from the Mars something? No, you know about what is boundary value. This is your electrical problem. All problems are defined by the boundaries and the values of the boundary. So, subject to the boundary condition, if I solve this, the solution is unique. That is called the uniqueness theorem. So, how do I prove it? You know that typical approach is I assume that there are two solutions to the process equation, phi 1 and phi 2. Both satisfy both some Gaussian. So I can write here equation 1 say del square phi 1 as minus rho 2 epsilon del square phi 2 as minus rho 2 epsilon because both are satisfying Gaussian. So if I take del square phi 1 minus phi 2, I get 0. Fine, that is from the typical result. But as I said, these are boundary value problems. So I assume that the values of phi 1 and phi 2 is phi 1s, s stands for surface. Phi 1s is equal to phi 2s. But now, on the boundary, if you take any boundary, it cannot have two different conditions. It should have a single boundary. Because you know the definition of potential. It's the work done to bring a positive charge in a positive charge from infinity to that point. And work done is independent of path, so it is a unique value. So that should be same. So boundary condition says that phi 1s is equal to phi 2s. Let's say it is equal to phi 2. So then I can always say phi 1 is minus phi 2s equal to 0. That's the boundary. Now I do a mathematical generally. This is mathematical generally. Equation 5.5. What is it? This is a vector identity, which is a very well-known vector identity that del of a scalar into a vector, the product of a scalar and a vector. You put the del of the vector into R, then you get the right hand side. I don't have to tell how it comes. This is typical vector identity. Now, what I am going to do, I am defining the scalar as phi 1 minus phi 2. Phi 1 is electric potential, so phi 1 minus phi 2 potential is scalar. And if you put a del on that, then del of phi 1 minus phi 2, which becomes a gradient, gradient, it will become a vector. So I define the vector as the potential gradient, that del of phi 1 minus phi 2. Then I simply put these two in equation 13.5. Then equation 13.6 looks very frightening, but actually it is very simple. It is just substitution of phi and d in equation 13.5. Then what I do is I integrate the entire thing over the volume V enclosed by the bounded surface S. As I said, this is the boundary value. integrating over volume V enclosed by boundary surfaces. So again, I write the same equation. See, look, it's same equation 13.6 written in integral form 13.7. Now, when I do that, I find that on the right hand side, or rather, first let's take the left hand side. It is like equation 13.8. Let's take the left hand side of the equation 13.7. It's a volume integral. By the way, I hope you have studied divergence theorem in your please go through the divergence theorem. It comes directly from the differential form of process. Differential form of process flow leads to the divergence. Now, divergence theorem you can have a lot of discussion, but to me it's a very simple equation. What does it do? It converts a volume integral into surface integral. That's the beauty of the method. That I can convert the surface integral to a volume integral into a surface integral apply divergence theorem. So I apply the divergence theorem on the left hand side of 13.7 and I get the right hand side of 13.8. But now since the integral is on the surface, all the quantities I put the surface value, but then phi 1 is minus phi 2 is becomes 0. So the left hand side of 13.7 I can prove and like divergence theorem that this is 0. Now naturally then right hand side will be equal to 0. Sum of these two terms. In this sum of these two terms on the right hand side of 13.7 you can see the first term has del square phi 1 minus phi 2. This del square phi 1 minus phi 2 we have already said by equation 13.8 that it is 0. So this right hand side of 13.7 the first term that del square phi 1 minus phi 2 that is also 0 13.9. So then effective to have is the second term of 13.7 which is written in 13.10 that is volume integral of this square of del of phi 1 minus phi 2 that is therefore 0 because all the other two terms are 0. When it happens that integral of a square of a quantity becomes 0, then you all know the how is it possible. Say integral of x square is 0. What is the solution? There is only one solution that x is equal to 0. So therefore, what you get is that the gradient of phi 1 minus phi 2 is 0 equation 13.8. It's a logical extension. Now, if I say the gradient of a quantity is 0, say gradient of something is 0, then can you tell me what is the property of that quantity? Quite
It's
obvious
constant. It is constant.
constant, right? So this is 13.11. So phi 1 minus phi 2 is constant. Now I have to find out what is this constant. But for that I have to apply the boundary. So I say that what is the boundary value? Phi 1 is minus phi 2. But then this is 0. So this constant is 0. Or in other words, phi 1 is equal to phi 2. Or in other words, that our initial assumption that there are two separate solutions to Gaussian equation, that assumption is actually correct. They are the same. That's the uniqueness theory. Now you can ask me that then why I am getting different results from different methods. The answer is very simple. That all these numerical only analytical methods are accurate because they solve it directly by solving the equations. Whereas numerical methods, there are, as I will explain it later on, there are always certain assumptions and so on and so forth. So no numerical method is actually 100% accurate. So the results that are different that you are getting are basically arising from the inaccuracies of the individual methods. So that's not the violation of uniqueness theory. This is a very tricky question sometimes asked in very good exams or papers or that is it a violation of uniqueness theory? Answer is no. This is not a violation of this theorem. These differences are coming because of the inherent inaccuracies of the individual. Stating that, then what are the procedural steps in the numerical implementation? For that, I would like to take a very simple example. Let's say I have a unit electrode and R. I want to calculate or compute the field. First question that I have to answer is where do I want to know the field? Is it inside the ionic electrode? Answer is no. Is it below the earth? Answer is no. Then we define something called region of interest. That means the region where I want to know the field. So ROI is the R. First thing in any numerical method is identification of ROI. Here I have given a flowchart that first I have to define the geometries, then I have to identify the R1. Now this is my ROI in this problem. But then theoretically in this ROI there are infinite number of points. I cannot compute at infinite number of points. That's not possible. That will take infinite time. So what I have to do, I have to compute at definite some finite number of points. But how do
হ্যাঁ
I get those finite number? For that we go for the third step,
আরে
discretization
স্ক্রিনটা
of
খুলে বসে
ROI.
থাকতে হচ্ছে রেকর্ডিং
To
করছি
discretize this region of interest, there are a lot of ways of discretization.
কি ক্লাস
That we
রেকর্ড
call
করতে
today
হচ্ছে
it is
আমাকে
called
আজকে
mesh generation. MESH mesh. That's another part of
খুলে bose থাকতে হচ্ছে অত সাথে
tools. There are so today such interesting mesh generators, and there are a
ধ্যাৎ,
couple of free
কি হবে শুনে
downloadable mesh generators. If you are really interested, download
একই
one or two
সাবজেক্টটা
and
আমার
then just
অনিচ্ছায় আমি
try
নিয়েছি
to use
মানে
it in
নিয়েছি
your
মানে দেয়া
laptop,
হয়েছে
and
আমাকে
you see how beautifully the
ফার্স্ট চয়েসে
generator
ছিল না
works.
এটা দিয়ে দিয়েছে
This is
আমাকে
all again mathematically done. Then you will understand the power of it. But anyway, for our practical case, what we do is the third step, discretization of alpha. And when I do the discretization, what I get are the finite number of points where I want to know the field. And these are called nodes, the field nodes. So we'll solve only at the field node. How do I solve it? I write the equations at these nodes only. So I write the field equations at only these n number of finite nodes. So the fourth step is creation of system of equations from the field, of course, the field equation. Once we do that, the next is definitely mathematics. This is solution system of equation. For that also there are so many methods nowadays. Numerical solution techniques. You can use those, and then you get the results. But results where only at the n number of finite nodes. But then anybody can ask that why only at those, why not some other? Yes, after the solution, I will do what is called post-processing of methods because the entire field computation will be based on certain fundamental assumptions. Using that, I can do mathematical interpolation and others, and I can know the results at any point. This is called post-processing. So basically, these are the pillars of the entire numerical field computation. Now, let me tell you again, give you a practical essence. Again, my own experience, personal experience. 1998, I was in Berlin in Siemens. I was working there, not as a faculty, I was a development engineer in 1998 in Siemens in Berlin. Berlin, they have a very big high voltage setup. I was working as a development engineer for developing a new insulator for their gas insulated transmission lines. That was at that time they were developing. One day I will tell you the story that how I landed up there from Colombo. That's another very interesting story. Anyway, I landed up there, I was working, and then I was in that design group. Then let me tell you how that design group actually worked. Then you will see that how practical life works. In that design group, there were a few people who were experts in CAD, computer aided design, CAD software. You know, wonderful CAD software. CAD software. So the first step that what we are saying now is definition of geometry. This will not be done manually. This will be done through CAD software. Because please remember we are developing something new, so the geometries are not known. So it is all started with the fundamental geometry and it will be an iterative process and it will be developed. So this will be done in CAD software, and in the CAD software itself we can identify the region of interest. And in the CAD software also we have a wonderful discretization. So this will be done in the CAD software. And then this will be transferred to the design elements. Now we are coming into it. But then when you say the design images, it's not only electrical. Don't make a mistake. When we are an industry is developing a product, there is very, very important aspects like because this insulator will be used in real life. So they have to withstand the mechanical pressure, they have to withstand the thermal stresses. So there were electrical design group like us, like me. There were mechanical design group like stress, strain, those analysis, then thermal analysis. So after the first three stages, this model will come to all these design analysts and electrical analysis, the mechanical stress strain analysis, the thermal analysis will be done, and then there will be a group. And in that everybody will present the result and then these geometries will be modified. But then interestingly what will happen is that electrical people will say, look, this radius is very small, you have to increase your radius. Immediately thermal people will start shouting, oh no, you cannot do that. If you do that, temperature will go up. So there will be a lot of conflicts. But all are valid. So what we have to do, we have to find the compromise. And a new geometry will be suggested. So it will go back to the CAD. Again, CAD people will design. Again, this model will be generated, discretized, and comes to the analysis. And these process go on and on. And after maybe 10, 15 iteration, finally, a geometry will be converged. Then that geometry will go for the prototype. Now, here comes the importance of the analysis. See, think about it that if all this iteration has to be done by making models, doing this, it takes maybe 3 years. But with this software analysis and all that iteration, all these things were done in 3 months. It's a huge, huge benefit for the industries. And also it helps in developing multiple prototypes quickly and then they will please remember one more thing. Once all this is finalized, that is never a product. So two, three prototypes will be finalized and then they will say the industry will make this and these are not models, these are actual 100% 1:1 model. And then they will be tested in the lab and it will be seen whether they are able to withstand it. And finally a product will come. And believe me, that is why these top companies, their products are so reliable because it goes through such a rigorous design process. And I have been a part of this because I have seen it in my life, and then I know how powerful this analysis can be. Sometimes people are skeptic about all these analysis simulation that those people do only analysis, they don't know how to do like a practical work. No, I'm not of that opinion. I know the importance of analysis and of course final decision will be based on the testing. Without that, no nothing will be final. This is the introduction part. Uh, Today I will not go into introduction part. Sorry, more than the introduction part. This note you will get, so don't bother about that. I will tell you, I will today conclude by telling one more story. That will, I hope it will be interesting to you. But for that, let me find out uh, another file. Let's see what it is. This is again I learned in another industry. 2002, I was working in a big corporate research in Heidelberg. Heidelberg is also in Germany. 2002, I was in a big corporate research in Heidelberg. And there, I had this experience. I will show you that. I see. See, there's something you will never expect. Here, correct. See, I will tell you this. I will share this. This is like I made in 2002 the chief transformer designer of ABB. Now, when I say that, please remember ABB doesn't only make only 11 transformers. They make real big transformers. They are very expensive. So when I met this person and they make such huge transformers for customers all over the world, so I asked him that how do you start designing of a transformer? You know, in Jadavpur, we give a lot of stress on transformer design. I hope you might have gone through that. Some, have you gone through
So
something?
we have done transformer design.
Yes. So now, if you remember,
Screen is not shared.
no, I have not yet shared.
Oh,
I'm telling that you have done transformer design, but if you recall your design, you started from where, right? You started from some efficiency, some flux density, some voltage regulation, so on and like those parameters. That were at the beginning point. And of course, what is the KV editing and voltage editing like that. That's how you started the design. When I asked this gentleman that how you start designing a transformer, now I will share my what the answer I got. Now you see on this. I hope it is coming. Has it come? Can you read it? What it is written here? What he told me? You believe it? What is the relevance? He say, must I appoint a photographer? I was shocked, and I thought that I know President. He said, why is it so like? And he explained. Then I understood that real life and just solving problem are so different. But
Sir,
then,
sorry, my net got disconnected. Sir, I could not follow, sir. Last few seconds.
no, I mean, what I'm saying is, you can read you can see this screen. Is it?
Yes, sir, I can see this thing.
So you can see what this chief transformer designer told me. You can read it, right? But
Yes,
my
sir.
but my question is, what a photographer does in the transformer.
Sir, maybe the size of the transformer, where
So
it will be fitted.
yeah, so then he explained it to me. But for that, I will show you the next slide. Now you see, This is a real big transformer. Can you see it? Now, if you can see my mouse moving, it is in the center. This is only the transformer without pushing or anything. And look how it is transported. This is manufactured in this background. You can see the manufacturing facility, the gray color, and this is being transported. And you can see this is given to me by Siemens. Siemens also. This is not it. Photograph is from Siemens. Now, when you look at this, and you can see there is a big hand standing here, and this hand is so small compared to the plastic. Now you can see that. Now, do you think that this vehicle can take a 90-degree turn?
No, sir.
No way, right? And moreover, this height of this transformer, etc., is important. So this gentleman told me that this photographer, what he will do is he will start from the gate of the factory and to the final destination, wherever it is. If it is transported by ship, then up to the shipyard. If it is to the customer's location, up to the location. And he will take all possible routes. He will try. And at every turn, he will take a photograph. At every bridge, over bridge, anything is there, he will take a photograph. And after that, he will come back and give it to us. Then my design team will sit and we will decide what is the maximum size that can be transported. Then he said that please remember I am manufacturing $1 million vehicle. If I cannot transport it to my customer, it will remain in my factory. The money is all down the drain. That's not possible. So before designing, the size is fixed. Now it is your duty, I mean, the designers, that whatever material you use, whatever frequency you use, whatever copper loss, bone loss, doesn't matter. But this is the size. If you design it bigger than this cannot be transported. I was never knowing it, but that is what explained to me with photograph. Then I realized that how I mean, what are the challenges of the real? But we should be geared up to that. Because if I am technically strong, I can do that. So that's what I always try to tell you that our life, when you do the work, is quite different from uh, from the boundaries of the educational institutes. So what is needed is you get your fundamentals strong. The moment you get your fundamentals strong, wherever you go, you will be able to develop yourself. Okay, so I think today I stop here. Anybody, if you want to ask anything, maybe 5 minutes you can also have, or otherwise you can close. Okay, okay, students, I think